This is section 1.4 and a little bit of appendix A. In your homework, I've added some review integration problems. That's appendix A, but I'm only going to talk about section 1.4 today, which is graphing solutions with Euler's method. There's a fun video here, and I put a link to it in Canvas. It's a fun video I created a few years ago explaining Euler's method with goats. Euler's method, suppose you can't solve a differential equation, first order differential equation, and that's actually happens more often than you would think. You can't solve it using the solution methods that we're going to learn in this class. I know that's a little bit depressing, but there are analytical ways to approximate the solution if you can't just flat out find it. And by flat out find it, I mean a closed solution. So what Euler's method does is it's sometimes called the tangent line approximation because it uses tangent lines to approximate the solution. So here's the formula here. It's an iterative process, which means you have to keep repeating the same process again and again, and at each step, you're going to use the results from the previous step. It's a little bit arduous to do it by hand. At the very least, you would want to write an Excel file that would do this for you, but we don't even have to do that because we're going to use Bluffton from the previous lecture. We're going to use that same site to apply Euler's method. Let me just explain how the method works. So we've got a direction field, and we want to approximate a solution that passes through a given point. So what we do is we start at a point, all right, and we remember, we don't know what the solution is, but we do know the slope of the solution at any point. dy dx is f of xy. So we compute f of xy. That will give us the slope of the tangent, and then x comma y is the point that we're going through. Hang on, my dog's having a nightmare. So we draw a tangent line at this point, and then we go a distance of h. So from this point to this point, we're going to travel h units, all right? And that's going to put us here. And then we do it again. We say, okay, well, what's the tangent line at this point? And the tangent line at this point, you can see it's got a slope that's a little less steep. So we're recalibrating. And we're going to stick on that tangent line for the next h units of x. So we travel out h units in the x direction, and we stop, and that puts us at this point. And then we say, okay, what's the tangent line here? We know the slope and we know the point, so I drew that tangent line, and we travel along that tangent line. You're getting the idea here, I think. And so as long as h is small enough, you'll be able to approximate what a solution looks like. If h is too big, you might do something crazy like jump solution curves. You might want to stay on this one, but somehow you end up on this one. That would be bad. So you want to pick small values of h. The default is h equal 0.1 in your homework and on the Bluffton site I'm about to show you. So let's look at Bluffton to do this problem here. And I've written everything down, so you really don't have to pay attention to what I'm saying. That doesn't sound good, but it's all written down. So let's go to Bluffton and look at how to apply Euler's method to the equation 2x minus 3y plus 1. And the initial condition is y of 1 equals 5. So you're going to go up here and you're going to enter the equation, and you don't even need to use time symbols. You can just write 2x. You don't have to write 2 times x, although it doesn't hurt, minus 3y plus 1. And then the default window is going to be -4 to 4, and then for y going -3 to 3. But remember, we want y of 1 equals 5. So we're going to go down to this second tab and enter 1, 5, but if I click submit, you'll see that the 5 is highlighted because it's telling me that 5 is outside the window that I want. So 1 is between -4 and 4, so I don't need to change the x, but 5 is not between -3 and 3. So don't switch that to 5 because that's not good enough. You want solutions that go past 5. So you want 5 to be cushioned, so maybe go to 6. Now, you don't care at all what the graph looks like because we're not using this for the graph. After you've entered your initial condition, make sure h is the value you want and don't click on switching. Euler will automatically be selected as the method. And then you're going to come down to this tab right here, Numerical Solution Tables. Click it, and then the values that you want are going to be right here. The y values are the values that you want. So your homework will prompt you, what is y when x is 1.1, 1.2, 1.3, and you're just going to pick those y values. So let me go back to OneNote. And so I've explained everything there. And then these are the guys you want. And that's about it. It's good to know what Euler's method is doing. The technology is going to do all the work for you. Since it's an iterative process, it requires a lot of work, but I want you to have some vague understanding of what that computer program is doing for you, because there are other approximation methods for approximating solutions of differential equations that are more accurate, but they're based on this type of thing. So if you can understand Euler's method, I think you'll be able to understand the other methods. And that's the end of this section. It's pretty short.